Next, I want to talk about one specific type of noise that can affect photonic qubits, and I'll be specifically talking about loss of the photon. So, photon loss is basically, when a photon leaks out of the fiber, for instance, basically it doesn't end up where it's supposed to go. And actually, mathematically, this is a type of amplitude damping noise, which we talked about previously. So, given that loss exists, even if we get the best fibers, there's still some chance that the photon will be lost. There still is protocols that exist that can help mitigate these effects of loss, even, and help to achieve higher entanglement fidelities, even in the presence of photon loss. And today we'll talk about one in particular called the Barrett-Koch protocol. So basically, I'll be kind of walking through what the Barrett-Koch protocol is. We also had a presentation recently, a couple weeks ago, by Michelle F. Adalero, where she uses our quantum simulator and our visualizer to visualize the Barrett-Koch protocol and other similar protocols. So I definitely recommend to check that out. Today I'll be kind of going over just the basics of what the Barrett-Koch protocol is. So the goal of the Barrett-Koch protocol is to establish entanglement between two nodes, even in the presence of photon loss. So we have our system, which will be these two stationary qubits at different nodes. There will be some two paths which connect them to a beam splitter, and then there will be two detectors, which are labeled here as D+ and D-. So our energy level for our stationary qubit will consist of three states. There will be a spin-up state, a spin-down state, and a excited state. So when the photon is, when the stationary qubit is in the excited state or in the spin-down state, basically a laser with the appropriate photon that has the appropriate energy can be used to basically convert, to basically kind of excite the stationary qubit to the excited state and also emit a photon. However, if your stationary qubit is in the down state and you shine this laser on your stationary qubit, no photon will be emitted because this transition will not be allowed due to spin-related rules. So the way this protocol will work, we'll start with each stationary qubit in a superposition state. We'll use a laser to excite from the spin-down state to the excited state. And then we will entangle each stationary qubit with a photonic qubit and then emit a photon. So if you're familiar with Brockhat notation, or if you've watched our previous webinar on quantum teleportation, feel free to follow along with some of the math that's sketched in here. Otherwise, you can also just follow along with the descriptions that we'll be giving as well. So our final state after step 3 here, we have basically some spin up and no photon, and portions to our quantum state, and then also excited state and photon portion to our quantum state for both of these two stationary qubits. So going back to our example, where we are so far in this protocol, we've entangled our photons with our stationary qubits, and we've just emitted our photons. So our photons are traveling towards the beam splitter, about to get measured. So now step 4, we wait for a photon detection at one of the photodetectors. So there's 3 possibilities here. There's a possibility that basically both of our stationary qubits emitted a photon, but the photons were emitted at slightly different times, and so when they travel through this beam splitter, they happen to go out of different ends of the beam splitter. In this case, we would want to restart our protocol because we're not actually interested in an entangled state where both of our stationary qubits emitted a photon. We want an entangled state where one stationary qubit emits a photon, but we don't know which one it was. If one detector clicks, we know that at least one photon was emitted and got through, but it's possible that we could have been in this state where 2 photons were emitted, but one photon just got lost. It's also possible that maybe both photons were emitted at the same time and experience HOM interference at the beam splitter and exit out of the same exit port of the beam splitter, but only trigger one detector because it's 2 photons hitting one detector will count as like one count. So in this case, this isn't great, or this is still not perfect, but this is like the closest to what we want. So we're hoping for this B case. And then C, there's a possibility that neither detector will click, which means that you might have experienced completely lost both photons, or neither qubit emitted a photon. So we don't want that to happen. So in this case, we would restart the protocol. So the next thing that will happen, will transform the excited state to the spin down state through local quantum operations on the stationary qubits. And at this point, entanglement will exist between these 2 stationary qubits, but it will be kind of degraded. It won't be the ideal entanglement that we wanted. So then what will happen next in this protocol, you can apply the X gate, which corresponds actually to a bit flip operation to both of the stationary qubits. And then we excite each quantum memory again, and now we wait for a photon detection again. If one detector is triggered, one photon triggers one detector. Now we know that our state is entangled in our desired Bell state, because as you can see from the state before this, we no longer have any chance of having this EE state because of this X gate operation that we've applied. So in the end of this kind of protocol, now we've been able to get much better entanglement. So here we've achieved perfect entanglement between our